All right, should I start? So I'd like to talk about the Dane surgery characterization of the unknown. So I'd like to talk about a theorem, and in fact, we have actually enough machinery to actually go through at least part of its proof in detail. So the theorem I want to state is, and this Cameron talked about, this was a theorem, and I think Zoltan mentioned this, well, it's the theorem which we first proved with Kronheimer, Mrówka, myself, and Zoltan. The theorem states that if P over Q surgery on a given knot is orientation preserving diffeomorphic, to the lens space LPQ, but let's just state it this way, to P over Q surgery on the unknot, then K is the unknot. And one should be careful here. The issue of orientations is actually important. For example, if you take the right-handed trefoil and do +5 surgery on it, then you get the lens space L54, which is minus L51, which is minus, if you like, +5 surgery on the unknot. So it's important that the orientation is preserved, and it's important that the surgery coefficient is the same. This has as a rather quick corollary that if some surgery on a knot gives you RP3, which is L21, then K is the unknot. Now, our first proof of this used, the proof that the four of us gave, uses Seiberg-Witten theory, and well, there's also an alternative proof using Heegaard Floer homology. I first gave a talk about this theorem at Stanford before any proof existed. And I said, you know, if we just have a little bit more contact geometry, then we'll have a proof of this using Heegaard Floer homology. And Eli Ashberg was in the audience, and I think he had already spent, this was a week conference in symplectic geometry, and he was tired because he'd already solved 3 or 4 outstanding problems in symplectic geometry. And by the time he heard my talk, he was just sort of exhausted. He said, yes, but what we need to prove this using Seiberg-Witten. So I said, well, okay, for Seiberg-Witten, you need to prove an exact triangle. Anyway, so we ended up, the 4 of us, proving the exact triangle, and proving this theorem, and we were very pleased with ourselves. And there was a conference in Banff, and the 4 of us gave lectures. We were very pleased with ourselves, and Yasha was in the audience. At the end of the lectures, Yasha said, yes, but why not you not just do this? And he did this contact geometry construction, which was the thing that was missing in the first place. Well, anyway. So now there are, I guess, two proofs. And of course, the construction that, the contact geometry construction has, of course, many other far-reaching consequences. But at any rate, so here's the statement of the theorem. I want to go through the Heegaard Floer discussion, though formally it's very similar to the proof using Seiberg-Witten theory. Okay, so right, what else should I say about this? So, well, of course, I should just remark that many cases of this theorem were already known. When Q is not equal to plus or minus 1, this follows from the theorem of Kohler, Gordon, Lukey, and Shalin. This is the cyclic surgery theorem. When P equals 0, it's a theorem of Gabay. This is called property R for knots. When P is equal to plus or minus 1, it's a theorem of Gordon and Lukey. So really, the remaining case that was open that needed to be solved was the case where P over Q is, of course, so the remaining case, so the open case was when the surgery coefficient is an integer which is bigger than 1 in absolute value. And, well, so I'm going to talk about that. Maybe I should also in fact, these ideas can be stretched to give alternative proofs of the case, rational case, except for this case. The case of Gabay gets actually somehow, some ingredient of his proof gets used in the proof of this theorem. So, okay. So, let me just say loosely what the sketch of the proof is. The proof is a two-step proof. Is there a question? Right. So the proof is a two-step proof. So there are two ingredients. And the first one is to show that if S3P of K is LP1, so I'm going to talk now about the integer case. If S3 of PK is LP1, then the Floer homology, HF plus, of S3 0 of K is the same thing as the Floer homology of S3 0 of the unknown. In fact, today I will show only that HF plus S3 0 of K, for all, that this is always trivial if I is not equal to 0. So the Heegaard Floer homology, the zero surgery in all the non-trivial spin C structures is trivial. And that's what I will show. And the second step is to show that if HF plus of S3 0 of K is HF plus S3 0 of the unknown, and this is going to sound silly, then K is the unknown. So the point is that we know something about the plus P surgery, then we conclude something about the zero surgery, and from the zero surgery we can conclude about the knot itself. In fact, the second step is something that I actually stated in maybe my first or second talk. Remember, I said that the genus of a knot, so recall that the genus of a knot is equal to the maximum integer such that the Floer homology plus 1 if K is non-trivial. So this is, well, maybe I shouldn't say recall. So steps more, in fact, this is the statement. And in particular, if star holds, then the genus of the knot must be equal to 0 or 1. And there's a special sort of song and dance one can do in the genus 1 case, but that's, again, actually not necessary because the genus 1 case has already been covered. So one could, we just put here 4 the case where the genus of the, it's known that the genus of the knot is not equal to, can never be equal to 1. This is a result of Goda and Teragaito. So star actually completes the proof of the theorem. So I'd like to give the details of step 1 and sketch the outline of step 2. So step 2 is kind of a long story, but and I can't possibly give all of its details, but I'd like to talk about it somewhat. So step 1, in fact, it boils down to an application of the exact triangle. But we need to have a suitable version of the exact triangle. And it's not quite the version that we've been talking about so far. So the exact triangle in the version I'd like to discuss is the following. Yes? The star holds, which says that flow homology is trivial for all non-zero I. Then you can conclude that the genus must be 0 or 1. Okay? So the proof is based on the following version. Is that clear? Is that okay? Okay.
So given the hypothesis that you have a one-space surgery, then this is equal to the genus is 0 or 1.
So given this hypothesis that the P surgery of K is LP1, we conclude that the 0 surgery has trivial Floer homology in all non-zero spin C structures. And from that, we then conclude that the genus must be 0 or 1. Pardon? And then it's not 1. Now, I mean, there's an alternative way of sort of handling with this, which is to say something more concrete about the 0th spin C structure. So you don't actually need to rely on that stuff. Yeah, any questions? Yes?
Yeah, I thought it plus I equal to 0, then because you get plus 1, you have to relate to 0.
I'm sorry, what's the question?
I for ATF starts from I equal to 0.
What do you mean starts from I equals 0? Oh, no. I'm sorry. This means the spin C structure. But when I write, my convention is that when I write HF plus, in fact, why don't I say this right now? That if I do plus P surgery on a knot, then the set of spin C structures on this space, I think actually Andrash already talked about this, this is identified with Z mod P. And there's a canonical identification, and the identification we can talk about as follows. If I take the 4 ball and I attach a 1 handle with framing P, then let BP of K denote the 4 ball union a 2 handle. Its two-dimensional cohomology is isomorphic to Z, and it's represented by, you take a Seifert surface for the knot K. So here's a Seifert surface for the knot K. I push it into the 4 ball and I cap it off. And F dot F is P. So I can look at the set of spin C structures of B4P of K is isomorphic to Z under the isomorphism which takes a spin C structure to the first Chern class of that spin C structure minus evaluated on this surface F hat minus P over 2. And the map from from spin C structures on this 4-manifold down to spin C structures on its boundary, which is S3P of K, is modeled on the map Z goes to Z mod P. In other words, in the case where P equals 0, which is the case that we're discussing right now, the set of spin C structures is isomorphic to the integers. And the way you construct that is you take your Seifert surface for your knot, you cap it off to construct a closed cycle that represents two-dimensional homology. And given any spin C structure, you evaluate the first Chern class on that cycle and divide by 2. You get an integer. And that's what I mean. That's what that I there is. Okay. Are there any other questions? Okay. So, all right. So the version of the exact triangle we would like to use is the following. Fix a spin C structure on the plus P surgery. That is to say, fix some J in Z mod P. Then there is an exact triangle HF plus of S3 mapping to HF plus of S3 0K, sorry. I want to take the sum over those I which are congruent to J mod P of HF plus S3 0K I, and that in turn maps to, HF plus S3 P of K J. Is that visible? No. That's too bad. Okay, then I'll leave it out. I hope that's visible. So, is that visible? Oh, that's not visible either. How's that? Is that visible? Okay. So that's to say, we take the Heegaard Floer homology of S3, we take a sort of a pth fraction of the Heegaard Floer homology of the zero surgery. That is to say, we take every pth spin C structure in the equivalence class J mod P over here for the zero surgery, and for the plus P surgery we take our fixed spin C structure. So you could write this up. This is, formally you could take the direct sum of all of these, and then it would look like you take P times the infinity surgery, the zero surgery, and the P over first surgery, which just formally looks like we're taking P times 1 over 0 over here, and we take 0 over 1 over here, and we take P over 1 over here, which is somehow, I don't know. Wow, okay. Never mind. This is the statement of the theorem. Okay, so the proof is basically the same as the proof before, but I want to say something important about this map from the P surgery to the zero surgery. This map from the P surgery to the zero surgery, this map is a sum of maps induced by the cobordism from S3P of K to S3. The standard cobordism from S3P of K to S3, which is gotten by, I do my P surgery here and then I cancel it with a 2-handle. Okay? So I sum all the maps induced by this cobordism, but I don't sum actually all of them. I sum those maps whose spin C structure restricted to the domain is in the jth spin C structure. That is to say, so let me just write this, let me erase this, call it A, and say, or AJ, and let me just say that A sub j here is the sum over all spin C structures in this cobordism W from the P surgery on K to S3 such that S restricted to the P surgery on K, well, maybe I should say it this way, so that the first Chern class of S restricted to that capped off Seifert surface minus P is over 2 is congruent to I mod P. This is just another way of saying that this, i.e., the spin C structure S restricted to the P surgery on K is supposed to correspond to our fixed J and Z mod P. And what am I summing over? I'm summing over F plus. Okay, is this clear? I think it's possible that all these, the notation is confusing, and I should just say it in words. We have a cobordism from the plus P surgery to S3, and that's got Z many spin C structures on it. When you restrict to the S3 P of K, those spin C structures fall into P equivalence classes, and we fixed an equivalence class. We sum those over those spin C structures that represent that fixed equivalence class. Okay. All right. So given this now, I'd like to sketch a proof of the theorem. So, our goal is to show that if I is not congruent to, if J is not congruent to 0 mod P, well, if I is not congruent to 0 mod P, then HF plus of S3 P of K, this is what I'm going to prove now, is equal to 0. Okay, so let's investigate what this sequence looks like. So, F3 is 0 of K. So, our goal is to show this. And of course, if S3 P of K is LP1. So, well, let's take a look at the exact sequence. So according to the exact sequence, the Floer homology, HF plus of S3 P of K in the J spin C structure is just, well, of course, it's just the Floer homology of the lens space LP1 in some spin C structure. So, well, in some spin C structure. Let me just write that as, so let's just say in the J spin C structure. So, actually, why don't I say it this way? So let's begin with the case where K is the unknot and there's no goal to show. But let's take a look at what the exact sequence looks like. In the case where K is the unknot and there's nothing to show, we already know that the plus 0 surgery all I not congruent to 0 mod P, we know that this group here vanishes identically, right? If this is the unknot. And this is HF plus of S3. So we have an exact sequence where that term vanishes, and this of course must then be an isomorphism. But what does So we're going to have to use the absolute gratings in a minute. But what is the HF plus of LP1 in the jth spin C structure look like? It's an infinite chain of z's and zeros connected, infinite chains of z's and zeros where the u action drops by 2, going in one direction, and similarly HF plus of S3 is also an infinite chain of z's and zeros. And we have an isomorphism, but what I want to say now is that what I'd like to do is I would like to calculate the degree, I'd like to calculate the degree of the bottommost element. In LP1, in the jth spin C structure. And I claim that all the information we have is already sufficient to calculate that. So the point is that the map from the plus p surgery to the infinity surgery is obtained as a sum of maps induced by cobordisms. And that is to say, you're summing over a bunch of different spin C structures. And what I claim is that the map A has the form, so we have infinitely many spin C structures over the cobordism from LP1 down to S3, and so these spin C structures S over the cobordism with C1 of S restricted to our surface F minus P over 2 congruent to 2I mod P, congruent to I mod 2P. But what I claim is that if I look at any K1 spin C structure, if I look at the map induced by this cobordism with respect to one of the spin C structures, and I try to compare it to the map with respect to the other spin C structure, they're always going to differ by some multiplication by some u power. And why is that? The reason for that is that that the map from HF infinity down to HF plus on a lens space is surjective. So now I'm going to use a little bit about maps on HF infinity. So first of all, the map from HF infinity to HF plus on the lens space is surjective, and similarly for S3. And the map induced on HF infinity by a spin C structure, well, it doesn't depend very much on the spin C structure because it depends on the choice of base point, but you can, if you move the base points around, as far as HF infinity is concerned, that's only going to modify this by some multiplication by some u power. So the maps induced on HF infinity don't depend terribly on the choice of spin C structure. So if I got some element over here, Xi, then I look at its preimage up here, I map it over here, and I map it down to here. Well, if I took a different power, then I would just be multiplying this by a different u power. So all these various maps just differ by u powers. And now, let's calculate, so I have some element here in some fixed degree. It's going to be shifted down in degree by some amount over here. Well, if it's a different spin C structure, it'll be shifted down a different amount. So what we want to do is we want to find the spin C structure for which this shift in dimension is minimized. So let's just do a little calculation. And so we've got our cobordism W here. What is the shift in dimension? So if I fix a spin C structure on W, the shift in dimension is given by C1 of S squared minus 2 chi minus 3 sigma over 4. But this is a two-handle addition that we're talking about. So its Euler characteristic is 1. Its signature is minus 1. And we're looking at C1 of S squared plus 1 over 4. But what is C1 of S? We said that C1 of S evaluated on our surface is supposed to be equal to 2i minus p. Well, that means that C1 of S squared must be equal to minus 2i minus p over p. So this is an exercise. And the point is that if this is true, then you calculate what multiple of the Poincare dual. So this is a rational number now. So this is going to be equal to 1/4 minus 2i minus p squared over p. And so our spin C structures are indexed by integers I, which are congruent to j mod p. There's a unique choice of I for which shift, so pardon? It doesn't matter, right? So we're fixing the equivalence class of j mod p for this equivalence class. So equivalence class, so we're fixing the equivalence class of I mod p. So we're saying it's j. So I is congruent to j mod p. And for this equivalence class, the choice of I between 0 and p minimizes this drop in dimension. In other words, the map from here to here looks like some, let's call that choice delta I. So in other words, we have this z over here. It's dropped in dimension by delta I, and all of the other maps drop by more. But all of the other maps are just, so I've got some element here, it gets mapped to some element here. All of the other maps map this same element to some u powers of this element over here. So that means that the bottommost generator over here must be mapped to the bottommost generator over here. Because if it were mapped any further down, this element would be in the kernel of this map, and we'd have some Floer homology class in HF plus of the zero surgery of the unknown. So that tells you that the bottommost degree element in this spin C structure has degree minus delta j. So let's not call it delta I, let's call it delta j. Okay. In other words, we've just calculated the degrees, so that is to say, so this exercise proves the following proposition. Consider LP1 and look at it LP1 and look at it in its jth spin C structure, and now look at the dimension of its bottommost non-trivial. If you look at HF plus, the grading of its bottommost non-trivial element is given by this formula which I just erased, which is P minus 2I minus P over 4P. Where I is congruent to J mod P, and I lives between 0 and P. So if J is not congruent to 0 mod P. Okay? Is that clear? Sorry, minus delta I. So it's given by minus this one. Let me just say this just again. We have a map from an infinite chain of z's and zeros, and an infinite chain of z's and zeros. And we have a map between them whose top order part drops degree by delta j, and it's that plus lower order terms. The statement is that, and moreover it's supposed to be an isomorphism. That means that the bottommost term here must live in dimension minus delta j. Okay? Is that clear? Yes or no? I want some feedback. No? Okay, so let me just say it again then. So I have a map, I have an infinite chain of z's and zeros, which stops. It's connected by some U action. And that's mapping homomorphically to another infinite chain of z's and zeros. And we're saying that this is a Q-graded space, and this is a Z-graded space. Its bottommost generator lives in dimension 0. And this map has the following structure. It looks like an isomorphism delta J plus lower order terms. But it's an isomorphism. That means, the sum of the whole thing is an isomorphism. That means that this term must get mapped to the bottom term here under this delta J. So this is a map that drops, or let's call it F delta J. So the F delta J is a map that drops degree by delta J. That means that this element must live in degree minus delta J, because it ends in something in dimension 0. Good. Okay. So we've now done this proposition, and we've calculated the Floer homology. So we've considered the case of the unknown. And now let's consider the case that we wish to understand. So suppose now that that K is an arbitrary knot whose plus P surgery is LP1. Now, I said that the fact that I've written LPK, that the fact that I've written LP1 as plus P surgery on a knot, that gives you an identification between spin C structures on LP1 with Z mod P. That may or may not be the same spin identification that you get from the unknot. So let me slough over that point, and let's just assume that it is the same. So let me just say a few generalities on the same argument. So let's now consider HF plus of S3PK in the jth spin C structure mapping to HF plus of S3. And again, we have an infinite chain of z's and zeros. Again, we have an infinite chain of z's and zeros. Only now, we don't know that this map is an isomorphism. What we know is that it looks like some term that drops degree by delta J plus lower order terms, but it may or may not be an isomorphism. And when I write Z's and zeros, I want you to think of this as the U module structure. So remember that there's a U action here, and this map is supposed to respect that U action. And now it's an exercise that a map between, so as a Z of U module, this is isomorphic to Z of U, U inverse, modulo Z of U. And so is this. And here's an exercise. A map of this type must be surjective, at least if we work over a field. If instead of Z's I were using a field, coefficients. Such a map would have to be surjective. It can only have kernel. And working over Z, of course, so, okay, it can only have kernel. It must be surjective. This is just an algebraic, or it's trivial. Now, we have over here HF plus of the zero surgery of K in the, well, this is the sum over all I congruent to J mod P. This is a finitely generated Z module. And again, maybe I should refer back to it. This is a basic fact which we didn't talk about, which is that the Floer homology of the zero, if Y is a three-manifold and S is a non-torsion, well, let's say Y is a three-manifold, and let's say its first Betti number, just for safety, is equal to 1, then the Floer homology of Y in any spin C structure is a finitely generated Z module. This is non-zero over the rationals. So this is a finitely generated module. So this map might be surjective. But what kind of kernel can a map of this type have? This is the zero surgery. This is the P surgery. This is the P surgery, and this is S3. And what we've just shown is that this map from here to here is trivial. This is surjective. This has some kernel. And what's the dimension of its kernel? Well, what we do is we look at the bottommost, take the bottommost generator here. Let's call that, this is a generator, the bottommost generator of HF plus of S3. Okay, so now of S3P of K in the J spin C structure. Let's call that, let's say that lives in dimension, not say minus delta, let's say epsilon J. Well, now you can see that, okay, so you might be a little confused because we just proved that epsilon J is minus delta J a moment ago. But so let's forget about the fact that we know that. But the point I want to make now is that I have a map from an infinite chain of Z's and zeros to another infinite chain of Z's and zeros. This chain of Z's and zeros stops in dimension epsilon, and the map shifts degree by delta. What is the dimension of the kernel? Well, you can figure out then what the kernel is. The dimension of the kernel, so let's suppose if there were no degree shift, the dimension of the kernel, if the degree shift, say, were 0, then the dimension of the kernel would just be minus epsilon, right? So suppose that delta is equal to 0, then then these elements would be in the kernel, right? And the dimension of the kernel would be minus epsilon over 2, right? The dimension of the kernel would be minus epsilon over 2, but there's also this degree shift upwards, and that's going to affect it by the bigger the degree shift is, the smaller that kernel is. So, so it's minus delta. Right? So if delta is really big, then this becomes a negative number. Okay? What's that? I'm now talking about the dimension. What's that? Epsilon is the degree. Delta is the shift in degree. And now I want to say that's related to the dimension of the kernel. So if epsilon is very negative, then the dimension of the kernel is going to be minus epsilon. And if the degree shift is very negative, if the degree shift were very negative, then it would also be the dimension. Okay? So we've now shown is that epsilon j minus delta j over 2 is the dimension of the kernel of the map from here to here. So that is to say, this group right here, this is a group of dimension equal to minus epsilon plus delta over 2. Epsilon j plus delta j over 2. On the other hand, but we just showed that the dimension of the bottommost generator in LP1, that is to say epsilon j, is equal to minus delta j. Remember, that's what we proved when we looked at the unknown. Thereefore, this group is always trivial. So the Floer homology of the zero surgery is trivial. Okay, this, yeah? Okay, so someone in the audience was on the ball. So there's a little funny business here. So let me explain the funny business. And the point is that the unknown induces an isomorphism between spin C structures on LP1 and Z mod P, and also K induces an isomorphism between spin C structures on LP1 and Z mod P. And we ask ourselves, how do we know those are the same? That is to say, so strictly speaking, we don't know that they're the same. There's some indeterminacy there. But what we know is that there exists some permutation with the property that, not quite. What we really showed is that there's a permutation with the property that epsilon of the permutation of j is equal to minus delta j. Right? So because I'm using the same j to index two different things. I'm using it to index spin C structures in LP1, thought of as surgery on the unknot, and I'm using it to index spin C structures on LP1, thought of as plus P surgery on a given knot. So what we really know is we know this. On the other hand, we did know that this is a group of this given dimension, and dimensions of groups are always non-negative. Well, that forces all the epsilons. That,
you replace the indices.
pardon?
It's epsilon
This should, I mean, no, the epsilon j is perfectly fine, but I should say then that this is minus delta sigma j plus delta j. But if all of those are non-negative, then this permutation must be trivial, and therefore I didn't lie. Okay? So that's a little, this point about the permutation is a little subtle point. It might not seem so, and it might seem kind of arcane from this point of view, but it doesn't seem so arcane if you look at it from the point of view of the lens space. From the perspective of the lens space, you have a knot in the lens space upon which when you do a surgery you get the S3. But you have a knot in it, and that knot has a homology class. So there's some indeterminacy in the choice of the homology class of that knot, and that corresponds to this possible permutation. So anyway, okay, yes? Yeah, so when I say there's a permutation, well, there's a permutation, but there are all sorts of restrictions on what kind of permutations are allowed. So they must be, they're very special permutations. They must fix the two spin structures, and they must respect the two-dimensional cohomology. I mean, I have an affine space for two-dimensional cohomology. I have to have a permutation that respects the affine structure. So, but I don't need to write all that up. I mean, for the purposes of this argument, it suffices to just say it's an arbitrary permutation. So, so we've now shown, so this proves what we wanted to show. This proves that if S3 P of k is LP1, then the Floer homology of S3 0 of k I is equal to 0 for all I not congruent to 0 mod p. And in fact, with a little bit of extra work, so with a little extra work, we can show this for all I not equal to 0. So the structure of the argument looks slightly different in the case where I equals 0, because in the case where I equals 0, this is no longer a finitely generated Z module. In that case, it's an infinitely generated Z module. There are two chains of Z's and zeros, and it follows that this map then must be the trivial map. And but those happen in the trivial spin C structure, and there are no other. It happens. There can be no other generators in any of the other spin C structures. So we've just shown that that HF plus of S3 0 K I is equal to 0 for all I not equal to 0, and therefore, and that completes step 1. Is that clear? Is everyone happy with step 1? So let me are you in the mood for some mathematical storytelling? So step 2, I can't lay out all the details because there are too many ingredients to talk about, but maybe it's just useful for me to kind of say, roughly speaking, what's going on. So for step 2, the question is, why does Floer homology of the zero surgery detect the genus of the knot? the first ingredient is this theorem of Gabai, who shows that the zero surgery detects the genus of the knot, in the sense that if I have a knot of genus G, then he constructs what's called a taut foliation on the zero surgery, which has a closed leaf that represents a Seifert surface with genus G minus 1. I'm not writing all this on the blackboard because I'm just going to write the final output on the blackboard. So Gabai constructs a taut foliation F, whose first, well, okay. And from that, there's a theorem of Eliashberg and Thurston. Let me just not say all the details. There's a construction of Gabai, there's a construction of Eliashberg and Thurston, and most recently there's a construction of Eliashberg and independently Ettenmeyer. And together what these things construct is the following. If I take the zero surgery on the knot, that's some 3 manifold. Well, the work of all these people put together constructs a symplectic 4 manifold, which is divided 2 by that zero surgery. And the first Chern class of the symplectic form restricted to the zero surgery, the zero surgery has two-dimensional cohomology isomorphic to Z, and the first Chern class of that restricted to the generator is equal to 2G minus 2. This is the geometry of what these guys have constructed. They construct a symplectic 4 manifold cut in half by the zero surgery, and the symplectic manifold is equipped with a symplectic structure whose first Chern class evaluates 2G minus 2 on the capped off Seifert surface in the zero surgery. And so this is a great deal of geometry, a great deal of hard work over the course of about 15 years or so. But then the second, maybe I shouldn't call that 1, maybe I should call it A. And then B, one shows that Heegaard Floer homology can be used to construct a smooth 4 manifold invariant phi from which is an invariant of a X4 is a smooth 4 manifold with B2 plus of X bigger than 1, and S is some spin C structures. And this smooth 4 manifold invariant looks exactly like Seiberg-Witten theory, so we conjecture that it is the Seiberg-Witten invariant. But, okay, it has the property that it has with 2 properties. And the first one is that for so here I mean the canonical spin C structure of the symplectic form omega. The invariant for a symplectic, if X is symplectic, then this invariant phi X omega is non-zero. And the second property is that if X is any 4 manifold which is divided in 2 by a 3 manifold, and phi of X is not 0, then the Floer homology, HF plus, of the 3 manifold is also non-zero. So this is a sketch of the ideas. So we've shown that, in fact, phi of XS if for a fixed spin C structure the 4-manifold invariant is non-trivial, then the Floer homology of the 3-manifold in the spin C structure that you get by restricting that spin C structure on the 4-manifold to the 3-manifold, this is also non-trivial. This is a sort of TQFT property of Heegaard Floer homology. The 4-manifold invariant of that 4-manifold goes through the Floer homology of this intervening 3-manifold. So if you put together A and B, you see that the Floer homology of the 0 Sergiev knot in the G minus 4th spin C structure must be non-trivial. And that's the sketch of how this argument works. I should say that an argument of this type has been used in Seiberg-Witten theory to show that the Seiberg-Witten invariant detects the genus of a knot by Kornheimer and Mruvka. And in fact, they proved such a theorem in '97 before the full force of this last result, the Eliashberg-Ettenauer result, was available. And when that became available, they were able to use this same structure, this argument, to prove property P for knots. So this is a sort of this route has been exploited a great deal. Okay, so that's what I wanted to say. Are there any questions?